Uh, good afternoon or good morning, wherever you are today. And I will just shortly say that it was a great pleasure to work with the team preparing this talk, and I think it will be very, very useful. We met and discussed this topic a little bit, and what we figured out that we actually keep learning from each other. So if anyone sees something that was missed or wanted to join our efforts, please contact us. And saying all of that, I will turn the mic to Jacalyn.
Okay, thank you, Katia. And I'm going to try sharing my screen. I will see if that works. Okay, so well, first of all, yes, there it goes. I'm going to be starting out with optimizing our code, and then later on we'll have some other people talking about how to profile the R code. But one of the things I wanted to begin with is what exactly do we want to say in terms of optimizing our code? What is our optimization or code optimization? So we want to look at what are the processes of making code more efficient. In general, when we say optimization, it can mean either optimizing with respect to time or respect to memory. What we're going to present will be mostly with respect to time, because most often we want to make our codes run faster. We're not as concerned about memory, although with big data we can be. But we want to focus today on how to optimize the time. Before I get started, I wanted to present some caveats to this. The first thing is we want to make sure the correctness of code is preserved. We don't want to change the code in the way that runs faster, but just gives us an approximation rather than the actual values that we want. The next thing is that the code should run faster on average. There can always be some examples where things will still be slower, but on average, will it make the code faster? And I think what's most important is there is a trade-off between your effort and the computer's effort. So for example, do you want to spend a week trying to shade 1 second of your code? Is that going to be an efficient use of your time? So we're going to look at what can you do, what should you do in order to make your R code run a little bit faster. So one of the things I'm going to look at is what are the basics for writing our optimal R code? What should you start with to make your code run as fast as it can? And I'm going to look at some of the things in R that are specific to R. If you're coming from a compiled language, there may be some techniques in R that you're not familiar with. You may be doing things the way you would in a compiled code. So instead of doing that, let's see what you can do in R. So let's just jump right in. The first thing is vectorization. If possible, you want to avoid using loops because everyone knows loops are where you can spend a great deal of time. And there are times when you will need loops, but overall you want to apply vectorization to avoid loops whenever you can. So the idea here is if you have a list of values or a vector, instead of pulling out each value and performing an operation, a mathematical operation on the individual values and then storing that someplace, you can apply the formula to the whole list of values. So in this example, and this is something I've seen a lot in compiled code where you want to maybe perform a mathematical operation on a list of numbers and sum the results. So you often start with your total or your sum being 0. And then as you complete each operation, you add to the existing total. And you apply, in this case, sine squared x minus 3x for each element. But in R, you don't have to do that to each element. You can apply sine to the whole list, and it does it element by element. You can square the sign, and it does it element by element. You can say 3 times the values, again, element by element. And then when you're done with all this, you can say, give me a sum of all of those elements. So again, vectorization is going to be very important for making the code run faster. The next thing is TidyVerse. TidyVerse can be used to manipulate data. It is a collection of packages designed specifically for manipulating data. It was designed by Hagley Wickham. Anyone who has worked with R knows that Hagley Wickham has made huge contributions to the R programming language. And it has a different approach to the syntax. So the example that I have here, I'm assuming that I have a data frame where I have a column with quality numbers, or numbers that indicate the quality of some data that I'm reading. And I want to average for each quality, I want to average another parameter or values from another column. So one of the things I might need to do is come up with a unique list of the quality values, find the length of that, create a set of zeros for the averages, go through each quality, come up with the row numbers that have that particular quality, and then average the column with the same row numbers. Or if I want to use TidyVerse, what I can do is just select all of these filters and pipe everything together. So I read in my data, and I'm reading it in as a data frame. I'm piping it into the filter that says group by, and I'm grouping it by the quality, the column labeled quality. And then I'm piping that into the summarize filter, which I'm basically telling it, I want to summarize by finding the mean of the column called chlorides. So, just comparing these two, you can see that TidyVerse is a lot cleaner in what you're going to be doing to your data. So that is something, not only is it cleaner, but it's also faster. So that's something that you want to look at. The other thing we want to look at is pre-allocating memory. And this is probably, next to vectorization, this is probably the one area that causes the most problems for slow code. In this example, what I'm doing is creating an empty list. I'm looping through a bunch of values, and depending on the values in my list, I'm applying some function to the value, either function 1 or function 2, and I'm appending the result to my existing list. So Y starts out as an empty list, and then each time through, I've appended something new to the list. So what's happening in that case is each time I'm appending the list, it has to go out and find some new memory for this larger list and store it there. So instead of doing that, what we want to do is go ahead and create a complete list for Y. I know Y is going to be the same length as the values that I'm sorting through. So I'm setting up a list where I have zeros already in all of those values. So it has created a list where I'm already allocating the correct amount of memory for the types that I'm saving in there. And then I'm going through the list. One of the additional things I have to do is keep track of the index and send the values into the correct slot. But overall, the amount of time you save is going to be worth that additional code that you see. The next thing, and this is quite common in R that a lot of people don't realize, is to avoid an overuse of parentheses. R treats parentheses like a function call, and it has some extra work that it's doing beneath the hood. So if you have excess parentheses in an algebraic expression, it's going to slow down the computation. The example I have is kind of an abuse of parentheses. The times I see this used most commonly is where someone says either x squared and they want to make sure it's known that they're squaring just the x, or another place where I've seen it commonly used is where you have an expression like sine x and you want to square that. A lot of times I'll see the parentheses around sine x and then the squared symbol. If you can remove those parentheses, the extra parentheses, it makes not only the reading of the equation a little bit cleaner, but it's going to make the execution of it a lot faster. Okay, the next thing is, and this one's going to be counterintuitive, use exponentials when you're squaring. And I've only seen this when squaring, not when you're cubing or using other powers. But in a lot of compiled languages, you're often told exponentiation is more costly than multiplication. So instead of saying y equals x squared, to say y equals x times x. That's not the case in R. The x squared is actually going to be faster than x times x. And also, more curiously, x squared is going to be faster than x times x times x times x. And I actually haven't found a good explanation. And if anyone knows of a good explanation of why this is faster, I would love to see that explanation. But I've run some timing tests and the squaring is going to be faster than multiplication. The next thing is, if you're ever using the unlist command to flatten a list, use it with setting use names to false. Even if you don't have names, or if you do have names, if you set the use names to false, the way it flattens the list is going to be significantly faster. And this is something you probably don't see. I actually just learned this week from Katia. So this is one of the things that you might want to remember to do when you're unlisting some of your data. The next thing is the if-else statement. Now, if-else a lot of times is used instead of a for loop, and it can be faster than using a for loop. But there are ways of getting around this where you can make things a little bit faster. So the if-else, if you haven't seen this before, what it's going to do is check this condition, apply the first value if that's a true statement, and the second value if it's a false statement. One of the things that's actually faster in this case is go ahead and set up your vector for all of one of these. You can pick one of the values. You can either set y to 1 or to -1. You want it to be the length of the vector x. And then replace, in this case, I'm replacing any position where x is greater than 10. I'm replacing the y value with a 1, because in this case, I originally set the y values to -1. And again, this is going to be much faster than doing the if-else statement. It's uglier, but it is faster. So those are all of the basics. And of course, there's a whole bunch of other operations you can do that that are common sense, like don't repeat a calculation 5 or 6 times. If it's a complex calculation, save it in a variable and reuse the variable. But a lot of those I assumed you already know from other programming languages. So I wanted to focus on just what would be unique to R. So up next, we have Rebecca and Gil. So I'm going to stop sharing. And I also wanted to add that at the end of all of our presentations, we will have time for questions.
Awesome, thank you, Jacalyn. So I'm going to go ahead and share my screen. So a bit like Jacalyn was saying is that definitely whenever you can, preallocate and vectorize. So in this little brief example here, we have a for loop that is basically going through the signed values of this vector. So in the very beginning, I have showing without preallocation, without vectorization, this takes, about 0.87 seconds. But if I preallocate that vector ahead of time with the amount of space and memory that I'm going to need, I can almost take a quarter of that time. And then if I vectorize, I can basically take 1/10 of the time, by simply understanding where to preallocate and where to vectorize. So this is just a very simple example, but really shows the power that can come whenever you can vectorize and whenever you can preallocate. Another thing to keep in mind is vectorized conditions. So one thing definitely, like Jacalyn mentioned, is that sometimes for loops, they can work, but it's really good to understand not to grow within a for loop. So if you're checking a condition inside a for loop, you can really slow down your time. But if you can vectorize with an if else, you get a little bit of a speed up. If you can vectorize the condition clause within the for loop, which is something that also Katia just told me about just recently as well, you can actually vectorize a condition inside the for loop. You get an even better speed up. But the even most fastest approach from these ones that we've at least demonstrated is that if you vectorize on the condition and the assignment, you can have an incredible speed up compared to the others. So definitely keep in mind what you need to vectorize, what you're hoping to accomplish, but just know, there are instances where you should be using a for loop. So if your input and output is scalar, where you have a single value that needs to constantly be updated, or if your iterations are sequential, or if they depend on each other, for loops are the way to go. It's just the best option in that case. However, if you have any other options where you don't need those two specifications, check out a function called apply. So apply is a function in R where X is your data. The margin can either be assigned to be 1, in this case is rows, 2 being for columns, or if you wish to do element-wise, you would do C1 and 2. But it's really, really incredible and powerful function that can also give you some speed up depending on what you're trying to do. Here's a really brief example about how the apply function works. In this case, I'm taking a matrix called counts. I'm assigning it to 3 columns. Very first one, I'm doing apply. I'm taking the matrix as my data. I'm saying, okay, I want you to look at the rows and I want you to give me the maximum of each rows. So here you can see it returns the maximum of each row. The second example down below, it's doing the same thing, but for columns. So give me the maximum from each column. And it's just a really, really nice, compact, efficient way of doing certain functions. And again, depending on what you're trying to accomplish out of your code can actually sometimes be faster than a for loop. Again, depending on what it is that you wish to accomplish. And also the really great thing about the apply family is that there's more than just apply. We also have lapply, which operates on lists and returns a list. This is incredibly powerful, especially if you're using data frames. This function here can actually return values faster than other functions such as row sum and column sum. In addition to that, we also have sapply, which simplifies your output. We have mapply, which passes in the arguments as vectors. And we have tapply, which also applies over subsets of data. So really, really handy functions, good things to know. Definitely give a look at them later and see if that's something you can use for your data analysis. And then with that, I'm going to pass it over to Gil.
Oh, hello. So the key advantage of apply is that it is this implementation of what's called functional programming. And what that means is that when we pass in the function as an argument, we can now apply it across all of the elements of our data. And so, but one of the nice additions to this is if we have multi-threading available to us, then we can very easily turn our apply functions into MCL applies. So in this example here, we're loading in the parallel library. And then what you see on the next line is the detect cores. Now, there's a caveat with saying detect cores. For those of us who are working on these shared cluster systems, detect cores is going to tell you how many physical cores are available, but this may not be all of the cores that you've allocated in your session. If somebody else also has cores available to them, you may still get all the cores, but physical cores shown, but not all the ones available. So just something to know about. But here, what you see is this linear mixed effects library has been loaded in, and then a function is defined, which is going to be f, which is going to be now passed to our apply function. And the first one you see, I run a system time, and I measure the amount of time it takes to run an lapply on that function. And then I just add 2 letters, MC, in front of lapply, and you can see that I've now got multi-threading available to me. Not great acceleration for 28 cores, but at least a little bit. Now on the next slide, what I'm going to be talking about is a sort of another way to do functional programming, but with the for each library. The for each library sort of combines the best of what you get from for and what you get from apply in this sense. It looks very similar to a for loop. You see, you say for each equals 1 to 3, and you have this do operator, and it's going to take the square root of each of those elements. But for each is a little unique in the fact that you can do these things like you can combine all the outputs together with that dot combine clause. You can see that I'm doing a column bind on all the results of getting four random variables from a normal distribution. The other thing you can do though is reduction. You can see if I do a plus sign for dot combine, now I'm combining those four numbers together. What this does is it allows us to do something we really can't do with apply, which is run a if we're in a loop across a group of scalars. So here you can see where I can do a combination of those, and I can even define with cfun a function of my own definition for doing a reduction. And there's all kinds of other things we can do with the multi-combine clause. We can take two arguments. Max combine can just tell us how many of the iterations we want to combine together. And in order, which kind of is going to give you a hint to what lies ahead, can even tell you whether you want to really execute these sequentially or not. Or they can be in any order. The default is true, but you can set it to be any order. So the last thing to show there is that %:% operator. And this is for the situation where we're nesting for eaches. And what this will do is collapse the nested loops all together and execute all those iterations in any order. So moving to the next one, slide, what you can see is I can load in the library do parallel, and now we have multi-threading available with the for each. What you see here is I've got a system time where I have a %do, and I'm running this across a sum of hyperbolic tangents from 1 to I. And then I just say register do parallel, and now I just replace my do with a do par, and I have multi-threading available there. So this is sort of yet another option for you if you're looking to multi-thread your loops. Finally, we just have this piece is really good. So a lot of your packages actually have this kind of parallelization already built in. So this is probably the easiest way to access multi-threading is just simply so what you see here is the very popular caret package I've loaded up here. And what you see here is all I'm doing is just saying library do parallel and register do parallel 28 cores. And I'm able to run it multi-threaded. Now you see that the time is actually a little bit worse than with the single-threaded version, but when I reduce it to 4 cores, then I see a little bit of acceleration. So the point is, you may already have multi-threading available to you with the packages you're using and not even be aware of it. And that's the point of this slide. And finally, we just have a slide with some additional packages we weren't able to get to today. I saw that the per map functions were mentioned in the chat. So those are certainly another option for functional programming. And I will pass this on to Katia.
Let me share my screen now. All right. Where I want to come from is I suspect that many of us are actually not necessarily writing our own code, but at least in my case, the researchers from BU come to me saying, well, here's my code. It has 1,000 lines, and for some reason it takes many hours, weeks, and sometimes in my case, thousands of centuries to run. And I do want to complete this research before I die, right? So we are not writing the code from scratch, but need to tune it enough so it would take reasonable amount of time to complete. And so keeping that in mind, I will take this approach. So when we talk about code optimization, we want to make sure that it runs faster and use less memory. I will touch base a little bit about memory because it is a great concern, but most of my presentation will also be related how to make the code faster. And so there are a number of tools already available in R to measure the time, which I wanted to mention. It's system time. There's a great package, Microbenchmark, rprof, and there are some functions that come with other packages, like you can trace mem. I believe it's still in base R, but there's also a very nice function ref to see the reference the reference tree reference of the memory, profmem, and profvis. And the basic function system time, I use it just to start to figure out how much time is spent by a particular chunk of the code. And one thing that I want to say here is that it is important to look at both elapsed time and system time. In this a very simple example, which will take a little bit of time, one thing that is concerning is the system time. Why do I even see the system time, right? And it's, as we will see later, it's because I'm constantly allocating and deallocating memory. So it takes some time to perform those operations. So our goal is to actually minimize both of those times, and specifically also it's important to minimize system time, which is easy to do, especially in this case. The other function that I mentioned is Microbenchmark, which comes from the package Microbenchmark, and it's especially helpful when we want to compare two approaches. Like it's not always obvious why if else runs slower than the example that Jacalyn was showing. So if you want to take a few approaches, you want to compare, and some of the majority of those functions take milliseconds or sometimes microseconds. So it's important to repeat them a few times to make sure that the results are comparable. And by default, Microbenchmark will run each line 100 times. You, of course, can override this default. And as you can see here, if my vector is large enough, this second approach is more than twice faster than a regular if-else statement. There are a number of profiling tools, and it is important to keep memory low, because one thing I want to say that, especially if you look into parallelization to parallelize your code, you can expect that depending on, of course, how you wrote the code and what type of parallelization tools you will use, the more cores you will use, the greater memory usage will be as well. So it's not rare cases when people in, at least at BU, have to decrease the number of cores, because otherwise they will not fit into the memory of the node, even if the node has 500 or even one terabyte of memory. So the functions like trace mem and the next function I will show you will help you to see where the copy of the object occurs. For example, in this case, you can see I define a vector A, and if I start tracing the memory of the object, I will see that even though when I copy A to B, there's no new memory is allocated, but once B is modified, then we will see that a new memory is getting allocated. Please make sure you keep in mind that trace mem slows down the program, so you don't want to leave that in your production code, and you want to untrace mem when you no longer need it. And in addition to that function, there's also a very nice function profmem, which allows you to get insight on when the memory gets allocated. So as you can see here in this example, the X is set to a matrix, and by default, matrix is filled with missing values. Not many BU researchers know that NA, regular NA, is actually has a class logical. So this X variable will be class logical. So then when I set X to be a numeric value modified, then what R has to do, it has to deallocate memory and allocate a new larger amount of memory. And as you can see, those allocation occurs, the allocation call occurs twice here. If, however, I fill matrix either with zeros or with NA setting a correct class of missing value, then we allocate memory only once. ProfViz is a great tool. As I said, I rarely write the R code myself. I'm normally a researcher comes and say, well, here's my code. And I never start with optimizing just those potentially very, very long codes. I first try to find the bottleneck. And let's first right now, don't even concentrate on the code right now. This is an example of usage of ProfViz. You put into ProfViz the code you want to benchmark to see if it's worth and where it's worth to put your effort. And by the way, in the slides, you can see I have also links about where you can find more information about that function. So if later on you want to follow up, you can do. So here for this code, you can see that ProfViz will show you that the majority of the time is spent in this line 7. So if you would like to improve the code, it doesn't make sense to start somewhere else. You want to take a look whether you can improve this. And what is not shown here, that ProfViz actually gives a very nice graph at the bottom where you can further take a look at the stack of the calls and figure out what exactly in this line 7 takes so much time. And it turns out is that subsetting the rows in data frame is a very costly operation. As you can see, this object data frame that I use here and where I omit rows is taking too much time. It's not optimal approach. So in this case, I then go and look what's stored in this data frame. And in this case, I realize that it holds all numeric values. And therefore, it's absolutely, there's no reason to create a data frame in this case. This should be a matrix. All right. The other thing, once this is solved, I can look at the next bottleneck line, and I see the example that both Jacalyn and Rebecca highlighted. You should not grow your array or data frame within a loop. So we want to allocate this object first outside of the loop and then fill it in. And then the last line I see here is this, something that, again, many Boston University researchers do not know, that when you either sample or do any other operation on random numbers, one by one or just a few at a time in a loop, it's significantly so much significantly slower than if you sample once as much as you need of those random numbers before the loop and then take them from the array. So here is, I rewrote the function. You can see I'm using matrix. I'm sampling before the loop. And so then within my linear model, I'm using the matrix. And I fill the resulting matrix with values. And I ProfViz again, and as you can see, everything is gone. We just have those 10 million microseconds to deal with the loop overhead, and we can further look at apply and other ways to improve. But all previous time gone completely. We don't see it in Profiz. There are many little tricks or additional ways to optimize your code. Both Jacalyn and Rebecca showed only a small number of them. If we had more time, we probably would be able to share more. But I also wanted to mention some further tools. Say you optimized your R code, and say it's still unreasonably, it takes a lot of time. You might want to look at these three tools: Rcpp, using GPU to accelerate your code, and compile your R with using either OpenBlast or Intel MKL. So I will just give you very brief introduction to these tools, and you can read further with the links. So I normally use Rcpp package when there is a loop that can't be vectorized, where each iteration depends on the previous iteration, but the code is actually, majority of the code is arithmetic. So if it's a basic arithmetic, if you don't really use much statistical analysis there, you can simply rewrite that code using Rcpp into C++, and the code, because of Rcpp, introduced so many convenient notations. The work that needs to be done is not that significant, but you gain a lot of performance gain. There are also, I would recommend, in addition to Rcpp, there are some other Rcpp family of libraries, so you can search and find more information. You can see in this example, we go from 8,000 microseconds to 400. So it's if you use that function a lot, it's worth doing this work. Another approach is to further parallelize your code in Cuda. In the example I gave you, it's a real example. The research I worked with was came from bioinformatics, and we put his code not just in converted to C, we converted it to Cuda code, and those 100,000s of centuries that initially was estimated to finish his work with, we finished with just under 2 days. And under this link, you will find the directions how you can compile your Cuda code and call from R. I was surprised it's something recent. They have very clear directions of how can be done, at least for the Linux systems. And the last set of links is how you can compile your R with OpenBlast and Intel MKL. So there are some manuals you can find in R, but also some directions that you can get in this website. And you can also look at the interesting package R OpenBlast. I haven't used that myself, but the package claims you can just use that package to compile your R with OpenBlast. With this, I want to make sure that we have enough time to answer your questions. So I will stop sharing, and I will just maybe give a couple of minutes for Jacalyn to summarize today's presentation.
Okay, let me just bring up my screen for that. Share my screen. Okay, so for final comments, one of the things I wanted to talk about is the optimization strategy. We usually tell our people to first write their code, make the code as efficient as possible from the beginning, but make sure that the code works after you have a working version of your code, you've debugged it, you know everything's okay, but you need to make it run faster, then you can start looking at some optimization techniques, some more aggressive ones, and you can use the profiling to find exactly where you need to optimize your code. For disadvantages, optimizing code is time consuming. So you need to kind of balance what are you trying to achieve and how much time do you have to do that. You should also be aware that optimizations can make the code harder to read and sometimes harder to debug. You should also be aware that different architectures will respond differently. So just because something runs faster on my laptop doesn't necessarily mean it'll run faster when I move it onto the cluster. I need to do the optimization on the cluster to get the best results. And then if you are planning on parallelizing, there are some optimizations that can adversely affect how you scale when you parallelize. So you have to keep that in mind. In terms of when to optimize, it is an iterative process. One of the things we recommend is that if your code is going to be widely distributed or used often by the research community, then you should take time to optimize it. If it's just something that's a one-off, it's going to run for a few hours, but you're never going to run it again, you may not want to optimize it. But you never know when your code is going to be used over and over. If you have a limited allocation on a cluster, you may want to look into optimization to make sure that your code is running in the least amount of time possible so that you're not wasting allocation on the compute resources. And then finally, when optimization isn't enough, if you've tried everything and it's still not running fast enough, you've got a couple of options there. You can either look for better algorithms. That's not always feasible for people today who are not writing their own algorithms, but using packages or functions that have been written by someone else. And then the next thing is to start looking into parallelizing your code. So having said all that, are there any questions?
So just one question. You guys mentioned the TidyVerse library. So these libraries are great making your code faster, but sometimes they decrease your code readability. And if you are working in a team and they have to understand your code and add to that, that also adds to the time to develop the code. So it's kind of goes in the other direction, optimizing the code. I just want to know your comment on that.
That's very interesting because some people that I've worked with have said that they like the readability of TidyVerse. And I guess it depends on how well you can write our code to make it readable to begin with. Does anyone else have any other experiences with TidyVerse?
I would say that TidyVerse is great for dealing with data cleaning, the usual, you get your dirty data set and you need to do some operations. It might not be as easy to use for, let's say, in some other areas, but I agree with Jacalyn. If you do use TidyVerse, generally I found that it's much easier to explain to people and to keep it nice and neat than a regular R approach. So this is, there are, in the chat, someone mentioned data table, which I really love to use for a very large data sets. It works greater and faster than a TidyVerse set of packages. But it's really, you have to have a mind of programmer to use it. That I rarely recommend for those people who do not have much R experience. But with TidyVerse, on my experience, it's much easier to explain TidyVerse than actually a regular R syntax.
Thank you.
Any other questions?
There were a couple of questions that we put into the notes. And I think at least one of them that might be of interest is sort of like generally how much speed up you can get, and some of you touched on this.
Yeah, I can say that it really depends. In many cases, I was able to get speed up many times, sometimes dozens times, sometimes 100 times. And when we go from that weird example from thousands of centuries to days, that's already, I would say it's a little bit of cheating because I actually go from R to another language. But within R, we just for the sake of times, we didn't show all the tricks and all the times, but let's say with unlist command, you go 100 times faster. With vectorization, depending on the length of the vector, it could be hundreds or thousands times faster. So it really depends on the code. But I would say it's I really enjoy optimizing it because it's just, you know, with the question, oh, should I go to the cloud? You know, I say, no, let's get down the memory usage. Let's optimize your code. And most likely you don't even need to use our cluster.
Right. And I've had similar experiences, and optimizing is going to depend on the system that you're running on and the type of code that you're dealing with. But I worked with a user on our cluster who her code was running in 36 hours. And she said, I really need this to run faster. And she approached us saying, can you help me parallelize it? And I looked at the code and it was a mess. And I said, well, let's optimize it first. And one of the things she did that was a no-no is she had a loop and was writing data to a file each time in the loop. And one of the things I suggested to her was she had enough memory she could accumulate all of that and do one write, because everyone knows IO is going to be a lot slower than most other things. And we did some other optimizations, but we went from the code running in 36 hours to running in 5 hours. And after that, she said, oh, I don't need to parallelize it anymore. This is great. So it is worth looking into a lot of these techniques.
Oh, one thing, the right steps, Jacalyn just mentioned that someone was writing into the file. One thing that I wanted to mention specifically for when you work in the cluster environment. There are sometimes where I see people writing into the file, appending to the file, either reading or reading line by line. You should never do that over the network. Let's say when you have your data in some project space and you do it in a local computer. That's first. You need if you want to read or write line by line, you should copy your data into the local machine. And more interestingly, if you do need to do that, as I said, as Jacalyn pointing out, that's in most cases it's not necessary. But if you still do need to do that, you need to know what I would recommend you to look at the write or read function that you are using. You can open the file just like you do it in C. Keep it open and then write or read using the pointer to for your file that is opened. Okay, so you, with this you will avoid opening the file, adding the having a number of seek records, appending the record, closing the file, and starting over again. You should keep the file open and add records to it. Okay, so that's this will keep the system time much shorter.
Yes,
Go
ahead.
I was just going to add that. So reading files, you should avoid opening so many files. If you open so many files, you open one and close it when you don't need it, and then open the next one and close it when you don't need it, because if you open many files, obviously it's a problem. And one other thing that I see is if you're a beginner, not worry a lot about writing good code on HPC. Just get it right on your desktop or on your laptop, have a good performance, and then think about the HPC and how the architecture is, then you can improve. If you understand how it works on your laptop, there is a better chance that you understand how it works on the big stuff, on the big computer.
Thank you. Yes. And I see we had a question in the chat about moving data to MySQL instead of SQLite. Whenever I've read data from a database using R, it's always because the database exists. So I haven't looked into which is more efficient in terms of storing the data and accessing it with R. So does anyone else have input in that?
I think the question was not the difference between those two, but just is there a time when it's better to deal with your data from a database via R rather than doing it all in native R? If that, Jeffrey, do you want to confirm if that's what you were asking?
Yeah, that's what I was asking. If maybe, and I did mean SQLite since that's in memory though. MySQL would be fine. Or also there's this module, is it RSQL? I don't do it too much because I do PandaSQL in Python, but I think they're pretty similar. And I was wondering if maybe there's some optimizations in RSQL that might be faster than, or maybe have integrated some of these suggestions. Like maybe it uses vectorization. I don't know. I'm curious about it.
Well,
I'll just jump in.
Go ahead.
I was just going to jump in because we've had some experience using SQLite on on our cluster, which is of course on the network, versus another data like MariaDB. SQLite, over the network, bad. In memory is probably going to be a better way to do it, and but then you always have to worry about getting it out of memory and onto disk for permanence. So, but you just certainly would like to hear what other people have experienced.
However, right now we're at 12:59, so it's time for us to close this call. And I really just want to give a big shout out to Gil, Rebecca, Jacalyn, and Katia. This was a great session. I learned a lot. I really appreciated hearing about optimizing and profiling in R. So heads up everybody, in December, it's not an hour, it's a 90-minute session, and it is the all-track social. The request from the organizers is make sure you've updated your version of Zoom so you can pick your breakout rooms and kind of build your own party the way you want it to happen. In January, our session is going to be on ways to measure impact, which will be a joint presentation with the emerging centers. I want to thank everyone who worked on the call. So that's Claire Mizumoto, Christina Koch, Wirwan Porwonto, Martin Kuma, Annalie Rugg, Amy Nesser, Katia Bulekova, Bob Freeman, and I'm Jana Nugent. Thanks for joining us today, everybody. See you at the party.